All right, so now we're looking at properties of limits to finish off this first section of limits. We looked at in previous videos just what a limit is. Remember, it's not the y value, it's what the y value is approaching. We evaluate limits with tables for the most part, but I did mention at the last video the fact that as long as it's a basic function, the y value is usually the limit, which is what we finished with. If you didn't get that, go back to that last video and rewatch that part again right at the end. That's important. Most of the time, we don't have to make tables. We can just plug in. If we have a piecewise defined function, can't really do that. Piecewise defined functions we need to deal with in other ways. But if I can plug in the number, if it's not piecewise, and I can plug in the value and I get a good number back, I'm not dividing by 0, then that's what the limit is going to be. So before I get to these properties here, just to derive that point home, let's say this first quick example, let's say we were looking at a very basic one like the first limit we looked at. We're looking at the limit as x approaches, say, 2 of the function 5x minus 1. That is a basic function. It's not a piecewise defined function. And as long as it's not piecewise, now this is a Krieger rule, so this is not a math rule you're not going to find in any book, but it's a rule that we can pretty much go with. That's pretty much anything we're going to see, it's going to work out this way. The limit as x approaches 2 of 5x minus 1 more than likely is going to equal whatever the y value is when x is 2, because it's a basic function. All I need to do is take that 2 and plug it in for x. Now, this is where we have to be careful, because we look at these and we treat them as the same. We treat this as the same as finding f of 2, which it's not. I'm not finding f of 2. I'm still evaluating the limit. It's just we have a rule that basically says that as long as we have this y value of this basic function, that's what it's going to approach. So 5 times 2 is 10 minus 1 is 9. That's the limit. Also, it's the function value, because that's how we figured out the limit. F of 2 is 9. These two numbers are the same number, obviously, but they answer two very different questions. Let me change that blue color. Let me go to, say, purple. So the one that I've highlighted in purple, that is the y value in x is 2. If I were to look at a graph, I would see a dot at the coordinate 2, 9. The blue one that I've highlighted does not say that at all. The blue one says that as my x values get closer to 2, 1.97, 1.98, 1.99, my y values follow a pattern that pattern shows that it's approaching 9. When I plug in 1.97, I get 8.97. When I plug in 1.98, I get 8.98. I'm not sure if I get those numbers. I'm just making them up so you can kind of get the idea. We could do the table on our calculator and see what those numbers actually are. But make sure you understand that even though these two work out the same, they look the same, they have the same answer, they are not answering the same question, and that is essential when you're looking at limits. Limits are all about what it's approaching, and it might approach what it actually is, but it doesn't have to. And we're going to see later in the next video exactly how that works, and that should really drive it home. But for the things that we're going to look at here, the limits we're going to look at, they are going to have y values, and they're going to be the same, and so that's going to evaluate a lot quicker. If we take a look at these properties real quick, I grabbed these properties straight from your textbook. We have b and c as our real numbers. We have two different limits, two different functions, f and f and g, and the limits are equal to L and k. What these properties do, all 5 of these properties, basically say that we can work with limits exactly how we hope we'll be able to work with limits, that the math works out and kind of makes sense. Other math makes sense too, but not to somebody who doesn't study it. It doesn't, like fractions can sometimes not make sense, even though to me and hopefully to you, fractions do make sense. I understand why we need a common denominator, but it doesn't necessarily work out like the super easiest way. These properties do. Scalar multiple. It just says that if I have, say, if I know the limit for, say, f of x is equal to x squared, if I want to do the limit of 5x squared, the scalar multiple just says, hey, just go ahead and multiply it by 5, multiply it by b, and you're good to go. Same thing with the sum and difference. We can do them individually. Just do the f of x limit and the g of x limit and just add them or subtract them. Same thing with multiplying, same thing with dividing, same thing with raising to a power. It makes evaluating limits much quicker if we have a given limit that we know, and that's what we're going to see here in our first example. So let's get that example up on the right side. Okay, so poof. Now we are looking through an example here. Given that f of x and g of x are given to you, we know the two functions. Find the limit as x approaches 5 of f of x times g of x. That's how you would read that. So again, it's not asking you what the y value is. It's asking if we were to create a table and look at 4.97 and find the y value, 4.98 and find its y value, 4.99 and find its y value, is there a pattern? And can we use that pattern to figure out what the next value would be when we actually get to x equals 5? Now, these are basic functions. They're not piecewise defined functions. They're pretty easy. You're just squaring, taking square roots. Square roots can be non-basic, and you'll get kind of a feel for things being basic and non-basic, especially as you take calculus next year and start seeing these even more in depth. You'll really see, how and when you can call something basic and not. And it's okay if you mistake those. It's not that big of a deal. To do these, according to the properties said that if you are multiplying, especially property 3, products, if you are multiplying two functions, then you can go ahead and find these individual limits and just multiply them together. Now, you wouldn't actually do all of this work. I'm going to write all this out so you can see how it goes, but in reality, you wouldn't have to do all of this. According to the property, I can do the limit as x approaches 5 of just f of x, get what that is, and then I can multiply that by the limit as x approaches 5 of g of x. I can do them individually. And so when I look at those and do those individually, I can do this purple limit first, and then after I'm done with that one, I can do this blue limit next, and once I have both of those, then I can go ahead and multiply those two answers together. So how do I get these limits? Well, first, the one that I've highlighted in purple, all I need to do is plug in 5. I don't have to go through that table process, because as I mentioned earlier a couple of times now, if it's a basic function, you can just plug it in. You'll know if it's not a basic function. Basically, if you get a number back, if it's not piecewise, if it's piecewise, you got to put on all the brakes. If it's not piecewise, if you plug in the number and you don't end up dividing by 0, you're fine. And so all I'm going to do is I'm going to go ahead and plug 5 into the function for f. That should be and will be the limit. And so if I plug 5 into the function f, that would be 5 squared minus 1. I don't know why I put it in parentheses. I just did. And that equals 24. So that is the limit as x approaches 5 of f of x. For g of x, I can do the exact same thing. For g of x, I can take 5 and plug that into the function and get the square root of 2 times 5 minus 1. 2 times 5 is 10. 10 minus 1 is 9, and the square root of 9 is 3. And so those are the two limits. In fact, I should write that out, and I will. 24 is the limit as x approaches 5 of f of x. We need that 5 in there. There we go. And then the other one, I need to write that one out as well. That is the limit as x approaches 5 of g of x. So by getting those two individual limits, now we can answer the question that we were originally posed. What is the limit as x approaches 5 of f of x times g of x? Well, that's simply going to be the limit for f of x, and the limit for f of x was 24, times the limit for g of x, and the limit for g of x was 3. And 24 times 3, if I do my math correctly, is 72. And that is the limit as x approaches 5 of f of x times g of x. This is how you use all of those patterns, or excuse me, all of those properties. All of the properties are used by simply just doing the individual limit and then putting it together whatever way it says to, by multiplying or dividing or adding or subtracting or raising to a power. So I've got just a couple other basic ones to take a look at. Let's do that on the next slide. Okay, so for this example, just really driving home this limit point, we're looking at the limit as x approaches 4 of 2x minus 6 over x minus 3. And so we want to see what happens when we plug in 4. Sorry, we don't want to see what happens when we plug in 4. We want to see what happens as we get really, 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 really close to 4. And so we could create a table. You can set up a table on your calculator and look at what happens at 3.97, at 3.98, at 3.99, and look for the pattern. Or you can just try plugging in 4, which is what we're going to do. We're not going to bother with that table, with that pattern. The last set of homework that I gave you, the first set that I gave you, 11 through 31, the odds, that's what I needed to see. I needed to see that table because we do need practice with that, and there is a purpose for the table. But for these problems, we don't have to do the table. We can just try what's called direct substitution. And so we're simply going to replace the x with the number 4 in both the numerator and the denominator. Everything else is going to stay the same. And then we just work it out. 2 times 4 is 8, and 8 minus 6 is 2. 4 minus 3 is 1. We get an answer of 2. This is not a piecewise defined function, and so as long as it's not piecewise, if you get a y value for your limit, that's going to be the limit. That is not a perfect rule, but pretty much everything you're going to run into, that's going to be the case. The tough part happens when we run into something like this example. Same function, but now let's take a look at the limit instead of x approaching 4. Let's look at what happens when we do the limit as x approaches 3 of 2x minus 6 over x minus 3. Now, if I try plugging in 3 in for x, I end up with some bad news, right? Everything else is going to stay the same. It's still going to be a 2 here, but instead of putting an x there, we're going to put a 3 in its place. Same thing in the denominator. Everything else is going to work out the same. This is still minus 6. This is still minus 3. Now when I try and evaluate this, 2 times 3 is 6, and 6 minus 6 is 0, and 3 minus 3 is 0. That's undefined. That is not our answer. This value is undefined because you're dividing by 0. But it doesn't mean the limit is that. To do this limit, because we got something that was undefined, the way that we have to do this limit right now, this is going to change in the next video, but the way that we have to do this limit right now, the limit as x approaches 3 of this, is to create a table of values. You would need to create an x and a y chart based on your calculator or based on your calculations themselves. Since we want to approach 3, we would look at 2.97, because that's far enough back. We can go as far back as we want. We can go all the way back to 2.8 and climb up from that. That's just too big of a table for me to write out. 2.97, 98, 2.99, 3.00, 3.01, and 3.02. We would then take these values and plug them in. Here's what you would let your calculator do the work, and here's what you get when you plug them in. This is going to look a little weird, but this is actually what you get. This y value is 2, this y value is 2, this y value is 2, so is this one, I should have gone one more. Let's go ahead and put that in there, 3.03. Right? And so if we look at the pattern, 2, 2, 2, based on this pattern counting up from 2.97 up to 3, it seems like we should get a 2 there. Based on the pattern counting the other direction, 2, 2, 2, seems like we should get a 2 there, and that is what the limit is. The limit is 2, even though when we plugged in 3, we got 0 divided by 0. It happens to be the same limit as the other one. There's reasons why this is happening, and we will see that in the next video. So, adding on to your homework from the last video. In the last video, I gave you page 768. I gave you problems 11 through 31, the odds, and with those, you need to have a table. If I don't have a table for those, I will not give you full credit. Or credit at all, which means you don't get the 10% grade bump. I'm going to add to that problems 51 and 52, as well as problems 55 through 73, the odds. On 55 through 73, the odds, no table required. You can just plug in and get the limit. Okay, so make sure your homework is correct, so when you email that to me, you'll get the full credit. So until our next video, stay safe and stay healthy.